In this lesson, we're going to have a look at solving simultaneous equations for AS Maths. So there's a slight difference to what we're doing from IG Maths. So we're going to have a look at where we're heading when we're doing these simultaneous equations at AS. Bear in mind that you've got two things for your simultaneous equations for AS. You've got just simply solving simultaneous equations, and you've also got working with the discriminant for simultaneous equations. So this lesson, we're just going to focus on solution. So when we have a line and a curve and we intersect them, how do we do that? Simultaneous equation. We'll do a separate lesson on how the discriminant works in with simultaneous equations and all the fun you can have there. So remember at IG, you had three ways that you would solve simultaneous equations. You had elimination, you had substitution, and you had graphical solution. So just to recap on the sort of things that you would look at under each of those. For elimination, you'd have things like 2x plus 3y equals minus 5, and 4x minus 3y equals 3. So you've got coefficients on all the x's and all the y's, and then we would solve by elimination. Coefficients. Seems like my spelling is a little bit dodgy today. On all variables. Okay, they're all greater than or less than 1. We're not dealing with that plain x, that plain y. When it comes to substitution, that's where our plain variable comes in. So we would have 3x minus 5y equals 7, for example, and 5x plus y equals 1. So you see where we've got that y that is sitting on its own. It's a plain y, coefficient of 1. And that means that we can make y the subject, and then we can substitute into the other equation. So here we have one variable as coefficient equal to 1. Our graphical solution, a little bit less calculation, a little bit more imagery, that's where we would actually have a graph. Let's say we have a quadratic and we have a linear, and then we would look for the solutions of the equations by where they intersect. So it would be those 2 points of intersections, and we can read the x values of our graph, we can read the y values of our graph, and we can get the solution to the equations. So obviously, as we're not using graph paper and we're focusing on sketching at AS, then graphical solution goes out the door. We're not going to be working with that. So the toss-up then is between elimination and substitution. Elimination may crop up every now and again. You might come across a situation where you're going to use it, but your focus is going to be on solving through substitution. The reason for that is that we are often solving a linear and a non-linear equation. And when it comes to linear and a non-linear, we can't do elimination because we can't add or subtract x and x squared, for example. Okay, so we have to use that substitution. So when we're solving simultaneous equations at AS, we are focusing on solving through substitution. Just a little note, remember that if you have something like y equals x plus 2, and you say y equals x squared minus 3x plus 6, this is still substitution. Okay, because you say that y equals x plus 2, and then you're going to put it here for the y, x plus 2 equals x squared minus 3x plus 6. So the only thing is that this is a slightly simpler substitution because you're not going to have to rearrange first. It still classifies as substitution. So we're going to focus now on doing some examples for substitution so that you've got a really good idea of some of the things you're going to come across. We're not going to bother with elimination. It's not saying you can't use it. You can use elimination if you come across a situation where it fits and you are a fan of elimination, then go for it. But today we're going to focus on substitution because we're going to focus on linear and non-linear. In order to do elimination, you would have to have two linears. So let's just make a note of that here as well. So here you would need two linear equations. So moving forward with some substitution examples. For example, if we had y equals x squared minus 3x plus 4 and y plus 2x equals 6. So first check, you have a curve, quadratic in this case, and a linear. So we are heading for substitution. We do have a y that is sitting on its own. So all is cool, we can just rearrange this one to get y equals 6 minus 2x. Now, if you're a person who has problem with these and tends to get things wrong, then show that minus 2x, y equals 6 minus 2x. Show all that algebra. Okay, with time, with practice, you should get the point where you can just rearrange. So we've got y equals, so if they're both y, they must both be equal. So we have 6 minus 2x equals x squared minus 3x plus 4. And now we're working only in one variable. So we can actually go ahead and solve this. So we want to move to have a happy quadratic, makes life easier for us. So 0 equals x squared minus 3x plus the 2x. So minus x plus 4 minus 6. So minus 2. You'll often find in a question like this, when you come across a quadratic, it is a simple one to solve because they're testing your simultaneous equations, not necessarily your factorization of quadratics. So we have an x, factors of 2 subtracting for 1, 2 and 1, bigger 1 negative. So we have x equals 2 and we have x equals minus 1. From there, we have y equals 6 minus 2 times 2, so y equals 2, and we have y equals 6 minus 2 times minus 1, y equals 8. So we've got two pairs of solutions. We have x equals 2, y equals 2, and we have x equals minus 1, y equals 8. Now the thing is here, we haven't been told that these are functions. We haven't been asked for coordinate pairs. So we just give our solutions as an x value and a y value, not as a coordinate. If we asked for a coordinate, then we would give that coordinate. So something slightly different. Let's work with xy equals 12 and 2x plus y equals 11. So we don't have that straightforward y equals ax squared plus bx plus c. Now we've got something fun going on. We have an xy. So obviously the only way we can deal with this is by substitution. Again, we have a plain one on our second one, on the linear equation, so we can just rearrange y equals 11 minus 2x, and then we are ready to go. Exactly the same idea, x, and instead of y, we're going to substitute 11 minus 2x equals 12. So that then opens up, it gives us 11x minus 2x squared equals 12. We want to work with a happy quadratic, makes life a little bit easier. So 0 equals 2x squared minus 11x plus 12. 12 and 11 slightly unusual, but the 2 is prime, so let's go ahead and factorize anyway. Factors, now of 12 that we could slot in here. We want to end up with an 11. So 1 and 12, 2 and 6, 3 and 4. 3 and 4, because then we would have a 4 and a 3. Because that would give us an 8 and that would give us a 3, and we're adding them, we get 11, but they are both negatives. So we get from this one, x equals 3 over 2 and x equals 4. Make sure you're happy with quadratics. They're going to come up over and over and over again. Okay, so when x equals 3 over 2, we use our rearranged one to make life easier. Y equals 11 minus 2 times 3 over 2. So y equals 11 minus 3, which gives us 8 again. So y equals 11 minus 2 times 4, 11 minus 8, y equals 3. So this question was all about those 3's and 8's. The solutions, we would have x equals 3 over 2, y equals 8, and x equals 4, y equals 3. So we're always giving our solutions to those simultaneous equations as a pair, because it's a solution for x and y, it's a solution for x and y. We wouldn't have y equals 3 when x equals 3 over 2. That is not a matching pair. So always be very clear in the solutions for your simultaneous equations. Another example. I told you we've got lots of examples for today. We have y squared equals 12x, and we have 3y equals 4x plus 6. So we're stepping up the intricacy a little bit. Not quite as straightforward. We have a y squared and we have a linear. Okay, so we have a curve and a linear, definitely going for substitution. But the thing is here, our linear doesn't have a plain variable. So we've got to think a little bit nicer. Do we want to make a y equals, or do we want to make it x equals? Now, if we make a y equals, when we substitute, we're going to have to square. And we really, really want to avoid that wherever possible. We want to keep our algebra as straightforward and simple as we can. If we make an x equals, we're going to substitute, and we're going to multiply by 12. If we make an x equals, we would have a fraction with a 4 underneath. It was going to cancel with that 12. So actually, that fraction we create is going to disappear straight away. So that's then the option that we want to go for. We want to keep life as simple as possible. So this one we would change, and we would have x equals 3y minus 6 over 4. Now we can go ahead and substitute. So y squared equals 12 times 3y minus 6 over 4. Because it doesn't matter if we solve for x first or y first. What matters is that we keep things as neat, tidy, simple, and efficient as possible. So y squared equals the 12 and the 4. We're going to get some cancellation there. So we end up with a 3 times a 3y minus 6. So y squared equals 9y minus 18. And again, we want to make our quadratic nice and happy to solve. So y squared minus 9y plus 18 equals 0. Now, of course, we're going to factorize. So we have a y and a y equals 0. Never forget it. Here's a crucial part. Factors of 18 that add to give 9. Well, that will be a 6 and a 3. Like signs, both negative. So we have y equals 6 and we have y equals 3. Then we get x equals 3 times 6 minus 6 over 4. So x equals 18 minus 6 over 4, which gives us 3. And we have x equals 3 by 3 minus 6 over 4. So x equals 9 minus 6 over 4, which is then 3/4. So our solutions again, let's actually not make things cramped. So solutions would be x equals 3 y equals 6, x equals 3/4, y equals 3. So this is just a case of the fact where we normally go in alphabetical order. So normally we would go x equals then y equals, sticking in that standardized format. So it's not an issue that first you calculated y first, then you calculated x, because we're now just stating our solutions. We're tidying off the end of our working out so that the solutions there are in their clear pair. Are we all happy with these examples so far? We've got a few more to work through, if everyone is good. Okay, all right. So we shall carry on. Let's change color. Let's get something different going. What if we have y equals 5 minus 8 over x and 2y plus x equals 4? So again, curve and a linear, substitution. So you've got to think, and you've got to think a few moves ahead. What's going to happen if I? What's going to happen if I? And this one, we've got two possible routes. Okay, we could go x equals 4 minus 2y, and then we would be substituting under the fraction. Or we could go y equals, we could introduce a fraction and then deal with the x fraction later. So at the end of the day, we are working through the same steps, whichever way we choose. So I'm going to choose to not work with a double term underneath a fraction. I don't want to do my x equals 4 minus 2y, then put my 8 over 4 minus 2y. I'm rather going to go, in this case, for y equals 4 minus x over 2. It's going to give me something slightly simpler when it comes to clearing my fractions. So I've got a y equals, so then I know that a 4 minus x over 2 must be equal to a 5 minus 8 over x. So of course, then I can clear my fractions. Now multiply by 2x one time. Clear everybody. So I would have an x, 4 minus x, equals 10x minus 16. And for me, that was a lot simpler than multiplying through by the denominator from the other rearrangement. So now we can open up, we can rearrange as usual. So x times 4 gives us a 4x minus an x squared equals 10x minus 16. We want a happy quadratic to make life easier for ourselves. X squared, 10x minus 4x, so plus 6x minus 16. And we factorize again. Factors of 16 which subtract to give 6, well, that's an 8 and a 2. Plus 6, so plus 8 minus 2. So x equals minus 8 and x equals 2. The more you practice with quadratics, the simpler and more straightforward they will become. When x equals minus 8, we get y equals 4 minus 8 over 2. And therefore, y equals 4 plus 8 over 2, y equals 6. And y equals 4 minus 2 over 2, so y equals 1. So in this case, we have our solution pairs. X equals minus 8, y equals 6, x equals 2, y equals 1. So even when our curve gets a little bit more funky, we are still working through exactly the same process and exactly the same logic of trying to keep things efficient. So we got one more to round us off for this lesson. Our final example. Y equals x squared minus 4x plus 7. 2y equals x plus 5. Now, I chose this one because this is something that you're going to commonly come across. Now, we said rearrange your plain x equals and substitute. But look at this case. In this case, if we were substituting for x, we would have to square and multiply. We want to keep things as simple and efficient as possible. We don't want to substitute in and square wherever possible. In some cases, you can't avoid it. If you have an x squared and a y squared, whichever you substitute for, you're going to end up squaring. But in this case, we can avoid it. Because in this case, we can say that y equals x plus 5 over 2. And we can substitute in for the y instead, and we don't have to deal with square. So we then get 2. X plus 5 over 2 equals x squared minus 4x plus 7. Clearing our 2, x plus 5 equals 2x squared minus 8x plus 14. Moving everybody, 0 equals 2x squared minus 8x minus x minus 9x. 14 minus 5, we have plus 9. So 0 equals 2x and x, because our 2 is prime. So factors of 9. 1 and a 9, we're not going to get anywhere close to a 9. A 3 and a 3, that sounds a lot more like it. So if we have a 3 and a 3, we would have a 2 times 3 is a 6 and a 1 times 3 is a 3. That sounds very good. Like signs, both negative. So we would then have x equals 3 over 2 and x equals 3. Using our y equals, as always, y equals 3 over 2 plus 5 over 2. Y equals 3 over 2 plus the 5 divided by the 2 gives us a 13 over 4. And on this side, y equals 3 plus 5 over 2, 8 over 2, y equals 4. So our solutions at the end of the day, x equals 3 over 2, y equals 13 over 4, and x equals 3, y equals 4. So always, 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 when you're solving simultaneous equations, think about what's coming. Plan for that efficiency. Plan for the simplicity. Don't go and take yourself on some big journey that's going to end you up on some long, complicated calculation, because the time allocation for this kind of work is based on that most efficient approach. You don't want to be wasting time. If you had done x equals and substituted for the x and squared and simplified, you would have ended up at the same answer. But you would have taken a whole lot more time and you would have had a whole lot more opportunities to make mistakes. And we really want to be avoiding that. So please, please, please think ahead and make sure that you are going the most efficient and the simplest route to solve your simultaneous.